Now tell me, my screen is visible to you? Say yes or no. Anyone?
Yes,
Yes,
sir.
sir.
Okay.
Yes, sir.
So we was doing the transistor. Okay. And that we saw the configuration like common base, common emitter, common collector. Today we will see transistor biasing. What is this biasing means? Biasing is a word that we use for the supply of suitable external DC voltage. It's nothing but the supply of suitable external DC voltage. So the biasing means what? If you're providing any external source, external DC voltage, then it is called as the biasing. And as we know that in case of BJT, if it is of NPN or PNP, we have three terminals, right? We have So we have this, suppose this is P type, N type, P type. We have three terminals, right? That you know. What is that? Emitter, collector, and base. And one terminal is emitter and base. Sorry, emitter, base, and collector, right? So what is that? We can keep either of these terminal common for input and output. For example, I am considering this is common base. So base is common for input and output, right? This is for input and this is for output. What is the biasing means? We are providing the external supply. What are that? Input and output input supplies. This is VEB. This is VCB, for example. So we are providing these external supply, and these external, if we are providing these external supply, this is called as biasing. So again, based on this biasing, we have four reasons in the process. What is that? We have first one is called as this junction is what? Emitter junction, JE, or you can say the junction between emitter and base, and this junction is what? The junction between the collector and base, so JC. So I'm just writing this is emitter junction and this is the collector junction. Okay, so if both are forward biased, if emitter junction and collector junction both are forward biased, this reason of operation, that means I am keeping this is P, so I am keeping as like this P2 positive of the terminal, and here also positive to positive terminal of battery. So this is forward biased, right? And this is also forward biased. This condition, when the emitter junction and collector junction both are forward biased, this region is called as the saturation region. Saturation region. In that case, the BJT will behave as an of short circuit or short switch. And in the next case, for example, our emitter junction is forward biased and the collector junction is reverse biased. This is called as the active region, and this is more popular reason. I will explain in detail. The third reason, the third possibility is what? Both are reverse bias. If both the junction are reverse bias, it is called as inverse active region. And sorry, if both are not, if it is forward bias and this is reverse bias, like that. If both are reverse bias, then it is called as the cutoff region. Cutoff region. Among these possibilities, when your emitter junction is reverse biased and your collector junction is forward biased, is not suitable for any application. So hence it is not used. It's a inverse active regions. We not used generally, it's just for the theoretical purpose. Okay. Now we will see in detail from the active region. I'm starting from the active region. We will go for the saturation as well as cutoff region. Okay. And this region, when this possibility, when your emitter junction is reverse biased and collector junction is forward biased, this we don't use it. Not suitable for any application. Now you start with the linear region or active region. Okay. Active region. And
Sir,
yes.
can you please scroll up for a second?
Okay. Fine.
Yes, sir. Thank you.
Okay. So first reason, that is active reason.
So
Yes.
which two are we talking about?
What happened?
Which two are we talking about for the for the regions?
For active reason. For biasing, I'm talking about the external supply that we are applying in the BJT. So there are four possibilities. Either both the junction are forward bias, both the junction are reverse bias, and like that, right? So based on this, we are going in detail. If, so for example, I'm talking about then BJT is working in the active region. That means the emitter junction is what? A forward biased, and the collector junction is a reverse bias. So what will happen? This, in this region, the transistor have many applications. That is the first thing. And this is also called as the linear region. Linear region. Why? Because the transistor in this region can work as an amplifier. Okay, so in the BJT, in this active region can behave as an amplifier. So most popular region will be the linear region or active region. What is actually happening? Suppose we have any BJT like this, which is common emitter, for example. This is base, this is collector, and this is the emitter. Okay, and for example, is this is the input IB. So what value of IC I will get? IC will be equals to beta times of IB. That is actually the amplification. We are providing IB and we are getting IC, which is of B times of IB. And you know the value of B is around 100. So we are actually increasing its value. Amplification we are doing. Okay. So this region lie between the saturation and cutoff region, and the transistor operate in active region when emitter junction is forward biased and the collector junction is reverse biased. And in the active state, the collector current is beta times of a base current or the input current. The second reason, that is the saturation region. In the saturation region, as I told you, both the junction, like emitter junction and the collector junction, both will be the forward biased. And in that case, the transistor will behave as a closed switch. That means if I draw it, a transistor, okay, I'm making one transistor, and this is a IB current flowing, this is the IC, and this is the IE. As both the junctions are forward biased, in that case, it will behave as a short switch. That means the value of IC is equals to IE. That means whatever you are providing, the same you are getting as the output. Okay. So in that case, in the saturation region, the collector current is equals to the emitter current. So in this region in which the transistor tends to behave as a closed switch, the transistor has an effect of its collector and emitter being shorted. And the collector and emitter current are maximum in this mode of operation. Now, in the saturation region, as I told you, it will behave as a closed switch so that you are getting the collector current same as that of emitter current. The third reason, as I told you, is what? Cutoff reason. Cutoff region means what? It will behave as an open switch. Open switch. So what will happen if I draw a BJT like this? Okay. And this is your collector, this is your emitter, this is your base, for example. it will behave as an open switch. That means you can draw like this. I and in between C and emitter, we don't have any connection. So IC is equals to 0, IE is equals to 0, and even IB is equals to 0. So in the cutoff region, all the currents will be 0. Okay, so you can write down that the collector current is equals to the emitter current is equals to IB is equals to 0. So, so these are the reasons on which you can work. So what till now we have discussed the different reason of operation for the transistor, but among all these reasons, we have found that the transistor operate well in active region and hence is also called as the linear region. So the output characteristic, if I draw the output characteristic of a BJT characteristic, see, this is IC and we are increasing the value of VCE. It will be like this for the constant values of IB. Okay, like this for the constant value of IB. So what is actually happening here? If I draw before that, there will be no current, right? And here in this region, the current is increasing, right? The current is increasing like this. So this is what a linear region or uh, a active region. In that case, the IC is equals to IE sort of thing. So it's a saturation region that we will go in detail. Okay, don't worry. Now, when the value, if I draw, so we want a amplification. So how we will get the amplification, that is more important thing. So we should know the concept of DC load line. What is that? When the transistor is giving some bias, some external output, and no signal is applied. For example, I am drawing like this. Here, I am providing a, for example, I am drawing a common emitter. Okay, so this is emitter, and this is the collector region, and this is the base region. Okay, I am giving supply here like this. Negative, positive, P and P. N to N. So this is forward bias, this is reverse biased. Okay. And this value we are assuming this is between collector and emitter. So it's a VCE. This is the resistance of a collector. So we are writing as a RC. This is the voltage between the base and emitter. So it's a VBE. Okay. We are not providing any signal. No signal we are providing here. This is the first case I am assuming when we are not providing any signal. And we are want to draw the line. What is that? DC load line. That means we are providing only the DC signal. Here there will be no amplification as there is no signal. But we can find out the value of the external output equation from here, which is equals to VCE equals to, sorry, this you assume VCC. This is VCC. And the voltage across the collector and emitter, you find out. This is VCE. Okay, so VCE will be equals to VCC. And for example, current is IC. So the drop will be what? Minus ICRC, right? So the voltage across the emitter and collector will be the supply that you are providing. For example, you are providing VCC here. So VCC minus the current and the resistance will give us the value of VCE. So this is the equation.
The, the
Yes.
negative minus VCC, no?
Minus VCC. VCC, yes.
Like, yeah, fine, sir.
Sir,
So
what is VCC, sir?
what happened?
So what is VCC basically, sir?
Is a biasing value. That is the external input output voltage that we are providing. As we have seen, we are providing the input and output voltages. Like here, we was providing the VEB, and this is this two voltages we have to provide. That is for biasing. Okay, so first is we are assuming this is one voltage we are providing, and this is the second voltage. Okay, so but there will be some resistance across the collector. So there will be some drop across this resistor. And if you have to find out the voltage across the collector and emitter, you subtract your output voltage that you are providing and output side voltage and with the RCIC. That will give the value of VCE. That is the voltage across the collector and emitter junction. Okay, so what, as you have seen, the output characteristic is like this. This was IC and this was a VCE. Okay, and we find out like this. Now we have to draw the DC load line. What is that DC load line? You have to connect with the I max, IC max. What is that? IC max. Okay, so here, if you see, if you put VCC equals to 0, VCE is equals to 0. If you put VCE is equals to 0, this is the equation. Okay, what is that? VCE equals to VCC minus ICRC. Okay, I want to know the value of IC if VCE is equals to 0. Okay, then what you will get from here? The value of IC will be equals to VCC divided by RC. Right? This will be the maximum value of current. This is the I max, you can say. In the second case, if in the same equation, if I put IC is equals to 0, so what you will get? VCE is equals to VCC, right? So now in this IC, if I connect from VCC by RC, which is the value of IC, maximum IC, and I connect with, as you know, VCE is equals to VCC, right? If IC is equals to 0, so this value will be VCC. So this is called as the DC load line. This is the DC load line. Now this is the procedure. Now you see what is the DC load line. As the VCC and RC are the fixed, right? The above one is the first degree of equation. Hence will be a straight line on the output characteristic. And this line is called as the DC load. So when it cuts the y axis and the x axis, you have to connect this line. This is called as the DC load. Okay, so when it will cut, when here in this case, as this is VCE, so if you put VCE is equals to 0, you will get this point. And when you put IC is equals to 0, you will get this point, right? In the equation. So by this, you can make a DC load line. And when this DC load line cuts your characteristic, when this DC load line cuts your characteristic, it is called as the Q point. This is called as a Q point. This is the best point for the amplification. If your BJT work in this position, like you will get some current and the voltage value. That means you will get some value of IC and VCE. If your BJT will have this current and the voltage value, then it will work as an amplifier, the best amplifier. Okay. So let's do some numerical based on it. So you will get the better idea what is actually we understand from here. Okay. So let's do some numericals. So what actually we started in the today's lecture, we have seen the reasons on which the BJT can work based on the biasing DC biasing. Okay. What is that? Whether your emitter junction or collector junction is forward, reverse, like that. Okay. And then we saw that this BJT can work as an amplifier. For this, you should work in the Q region. Okay. Q point. For how you will calculate this Q point by joining the by connecting this value, this when your VC is equals to 0, so you will get the value of IC, and when IC is equals to 0, you will get the value of VCE. If you connect it with the straight line where it cut, you will get the Q point. Okay. Now, how you will get the numericals? Let's see. First, you solve some easy questions. Okay. First question. Suppose in a common base, they are writing common base. They are giving alpha is equals to 0.95, and they are saying that the voltage drop across. Okay, I draw the circuit, that's better, right? So here we have a BJT, okay, and this is IE. This is suppose IC, and this is VCB, for example, and I am drawing the common base. This is 2 kilo ohm, and they are saying the voltage drop across this 2 kilo ohm is 2 volt. Find out the base current. Question is what? You have to find out the value of IB. So tell me how you will find out. This is the figure that is given. So what you will do? Here you know the voltage drop across this 2 kilo ohm resistor is 2 volt. So can we find out the value of IC? You know the resistor, you know the value of voltage. So what you can find out from here? The value of IC. IC is equals to what? Tell me the value of IC.
1 million.
Yes, is 1 milliampere. If you know the value of IE, and alpha is also known to us, that is 0.95. So the value of IE will be equals to IC by alpha, right? That you know. So it will be 1 milliamps divided by 0.95, and you will get some value. Tell me that value.
One point zero five.
Yes, it's 1.05 milliamps. And we have to find out the value of IB. So how we will find out? As you know, the formula is that I is equals to IC plus IB. So from here, you can find out the value of IB. You know the value of IC, you know the value of IE. So the value of IB will be what?
0.05 milliamp.
0.05 milliamps. Okay, so this is one type of question. Now you see the second question. Question is like this. They draw a transistor. RC they given 1.2 kilo ohm. VCC they have given 1.8 volts. This is the value of IB. This is RE, that is 1.5 kilo ohm, and VEE is equals to 8 volts. So this is common base circuit. Okay, and they said that find out the value of IC and VCB, the collector to base voltage. Assume that the transistor is made from the silicon. Okay, that was the question. Now you see how we will find out. We will apply a loop here. Okay. This is IB, so here the current will be IE, and here this will be IC, right? So if I apply the loop here, what you will see, this is VEE, right? So VEE is equals to, the current is what? IE, and this resistor is RE. So it will be equals to IE, RE, and this is the emitter junction, this is the base junction. In between them also we have a voltage that is called as the VEE. Okay, so plus VBE. In this manner you have to write down the equation. Okay, so in this loop, this is the voltage VEE, this is the current IE into RE, and there will be a voltage drop across the base and emitter region also. Okay, so from here we can find out the value, and also as this is a silicon, the value of VBE is fixed as 0.7 volt for the silicon, and the value of VBE will be 0.2 volts for the germanium. That is fixed. Okay, so if you know all these value, can we find out the value of IE? IE is equals to VEE minus VBE divided by RE. VEE is what? 8 volts. And VBE, as I told you, as it's manufactured from the silicon, the value will be 0.7. And if it is germanium, for example, then you have to put 0.2. And RE value is what? 1.5 kilo ohms. So what value of IE you will get?
milliamps.
Yes, 4.86 milliamps. Okay, so this is the value of IE. Now we can assume that IB is very small. Okay, I'm assuming this IB is very small. Now I'm applying for this loop. Now I want to apply in this loop. So if in this loop, again, I'm writing the equation. Okay, so what is that? VCC is the supply that we are providing. Here the current is what? IC, and in the across the register is RC. So it's equals to IC into RC plus, again there will be a voltage drop across this base and collector. Okay, so this voltage will be called as VCB. Okay, so VCC that we got is what? 18 volt. So you just put 18 volt here. I assumed IB is equals to 0. In that case, the IC will be equals to IE, and that is equals to 4.86 milliamps, right? So you can put 4.86 milliampere, sorry, not volt, milliamps here, ampere, and RC is what? 1.2 kilo ohms. So you can multiply with 1.2 kilo ohms plus VCB. Can you find out the value of VCB from here?
Sir, 12.168.
1 minute.
Yes, sir.
12.168. 12.168.
So what are we trying to find ultimately? This
Actually, in
question.
that question, they asked to find out the value of IC and the VCB.
Okay. And through IE, we found out the value of IC since both are
Yes.
equal.
because we assume that the base current is 0.
So how can you
We can always assume this if it is not given that the
If it
base.
is, yes, base current is very small, so you can assume this as 0 if it is not given.
Okay, sir. Thank you.
Okay. Now you write on the next question. They said that it's a common emitter configuration in which the collector supply,
Excuse me, sir.
yes,
So VCE will be VCB minus VEB, right?
VCC is equals to, what is that?
VCE.
VCE. Here, see, this is common base configuration. Don't confuse, this is common base configuration. So there will be a connection between base and emitter and the collector and base. So here you can find out the common means VCB. Okay, let's see in the next case, you will have this VCE. Okay, are you getting? This is common base.
Yes, sir. Yes, sir. Got it.
So now this is common emitter. Okay, now I'm talking about common emitter configuration in which they said that the collector supply is 8 volts. Okay, and they said that the voltage drop across the resistor, voltage drop across the resistor. What is that? RC resistor. Okay, RC, that is the collector resistor, is 0.5 volts. And they also gave the value of RC is equals to 800 ohm. Alpha is 0.96. And they said that find out the VCE point and also find out IB. That are the 2 points that we have to calculate. And they gave so many things. They have given the collector supply, that means VCC they have given. Then they said that the voltage drop across the RC is 0.5 volts. They gave the value of RC, that is 800 ohms. Alpha is also given to us. So what is the first step? You always draw the circuit. Okay, what is that? Like a, so here you can make one resistor, that is RC. Okay, and this is VC C value that they have given 8 volts. And they also said this value is 800 ohms, where the voltage drop is 0.5 volts, right? And as this is common emitter, this will be IE and this is IB. And for example, as this is the base voltage, so I'm assuming this is a base VBB. This is the collector junction, this is the emitter. Okay, so the voltage around it will be your VCE, and that you have to calculate it. Okay, so this is the VCC. This voltage we need to find out. This is RC, this is the voltage drop, and you have to find out the value of IB also. Now, if I apply the looping here, that we already know that VCC equals to VCE plus ICRC, right? Or in other words, we can say this is VCE is equals to VCC minus ICRC. Right? So here the VCC is what? 8 volts minus the volt. Either you multiply it with IC. IC we don't know. We directly know the voltage drop. So you can directly write 0.5 volts. Right? This is the voltage drop. Either you can, if you know the value of IC, you multiply with IC. Otherwise, if directly voltage is given to us, you can provide direct voltage. So it will be 7.5 volts. This is VC. Right? Now, can you find out the value of IC?
Sir, I have a doubt, sir.
Yes.
So shouldn't it be VCC plus ICRC?
See, this is the supply voltage. Okay. Definitely there will be the voltage drop across this will be the sum of this. Okay. So this is supply voltage. You have to assume this will be the sum of these two, the voltage drop and this the current across this resistor.
Sir, but KVL shows differently, right? Like
So
it shows VCC
see,
plus.
they say in the numerical they didn't told us anything about this polarity. They gave only
Okay.
the value of voltage. Okay. So in that case, if they are providing the polarity, you can go with the KBL. But they are not telling us anything about the polarity. They are saying that this is the input voltage. This is the voltage that is the collector voltage they are providing. 8. So in
Okay.
that case, you have it. Okay.
Yes, sir. Yes, sir. Got it.
So here you find out the value of IC. IC is this one. This is equals to voltage divided by resistor, right? So here it will be 0.5 volts divided by 800 ohms. So it will be 0.625 milliamps. Now beta is dependent on the value of alpha. Alpha is given to us, that is 0.96. So it will be what? Alpha divided by 1 minus alpha, right? And alpha, you know what is that? 0.96. So 0.96 and you will get 24. And IB is equals to what? IB, IC by beta. Yes, IC by beta. Right, correct, na? IB is equals to beta. Yes, correct. So it will be 0.625 divided by beta that we calculated as 24 and you will get the value of IB. Tell me the value of IB. After this, what
So
you will get?
0.25. So
Okay,
0.025. Yeah.
0.025 milliamps, right? Because it was milli.
Yes, sir.
Yes.
0.026. Sorry, sir.
Okay, now next question will be based on DC load line. Okay, we have already seen the theory. So, for example, they gave one diagram. Okay. And they have you have to draw the DC load line. DC load line. Question is based on DC load line. 12.5 volt is the supply voltage, and for example, this is VBB. DC load line, for this you have to assume that there is no signal, and that will be like this, and this is one BJT direction of current like this, and this is 2.5 kilo ohms. This is a value of RC. So whenever we have to find out the draw the DC load line, how you will do? You just apply here and write down the equation. What is that? Always VCC, okay, VCC equals to VCE plus ICRC. Okay. And for the DC load line, as I told you, you have to connect like this. In this condition, if you're drawing the value, if you're plotting IC with VCE, how I will get this point? When VCE equals to 0, right? And when how we will get this point? When IC is equals to 0. So just put for the first condition when IC is equals to 0. Okay. So if IC is equals to 0 in that condition, in this equation number 1, what you will get? VCC is equals to VCE, or you can say VCE is equals to VCC. Both the things are same. Okay. In the next case, how we will get the second point? when your VCE is equals to 0, right? In that case, the original equation was what? VCC is equals to VCE plus ICRC, right? I'm assuming that VCE is equals to 0. So the value of IC will be equals to VCC divided by RC, right? Now tell me the value of VCE. VCE, the first case when VCE is equals to VCC, we know the value of VCC, right? Tell me the value of VCC. Anyone?
So can you scroll up for a minute? Because I just want to
Yes.
see the circuit. So the VCC will be 12.5 volt.
Yes, so it will be 12.5 volts. Tell me the value of IC.
So 5 milliamps.
So that will be equals to 12.5 divided by what is the value of RC? 2.5, right? It's 2.5. So it will be what?
5 milliamps, sir.
It's 5 milliamps, right? So how to draw the DC load line? Here you just make a IC here, that is the collector current, and this will be VCE. And you just connect here. This value will be 5 milliamps, and this value will be 12.5 volts. Okay. Now, next question. This is how we can draw the DC load line. Now, in the second question, they said if VCC is 12 volt and RC, that is the collector resistance, is 6 kilo ohms. They said that draw the DC load line. That is the first thing, DC load line. And then they are saying, what will be the Q point if zero signal base current, if zero signal base current, that is the IB, is equals to 20 microampere and beta is equals to 50, right? This is the question. What is that? They are giving that the supply is 12 volt. RC they given is 6 kilo ohm. First, you have to draw the load line. That is the first thing. And then they are saying, what will be the Q point? You have to find out the Q point. If zero signal, of course, in the DC load line, you cannot provide the signal. And the value of IB is given as 20 microampere and the beta value is 50. So first you find out the equation. Okay, so I'm just drawing it first, the circuit. Okay, and suppose this is a common emitter. Okay, so this is emitter, for example. There we are not providing any signal, and I'm drawing it. Okay, this is the last page. Okay. So if you draw like this, and you are not providing any signal, and this is a VBB, VBB. And they said that this is the value of RC. RC they given 6 kilo ohms. And here you are providing the VCC, which is around 12. Like that, you have to assume it. Okay. If I write down the equation, this will be what? VCC equals to VCE plus ICRC, right? First step is what? Assume IC is equals to 0 and find out the value of VCC equals to VCE, or in other word, I can say VCE is equals to VCC. VCC is given to us. What is that? 12 volt, right? So in that case, it is equals to 12. Now, in the second case, when VCE is equals to 0, the value of IC will be equals to VCC by RC. And this VCC is 12 volt, RC, RC is 6 kilo ohm, right? So you can give here 6 kilo ohm and you will get 2 milliamps. So by this you can draw, yes,
Was it mentioned that IC is 0?
IC.
Yes, sir. Was it given in the question that IC and VCE will be 0?
No. For drawing the DC load line, DC load line, how you are drawing? You have to connect the x-axis and y-axis. In the how you connect it here, when your IC is equals to 0, right? And in this condition, when VC is equals to 0, this is the y-axis, no? This is the x-axis, right? And this is the value of IC. So if you want this point, how you will get this one? When your VC is equals to 0, so you will get this point. And when your IC is equals to 0, you will get this point. For this, we are finding because we want these 2 points. Then only you connect and find out the DC load line. Okay. So for finding out that points, we are assuming that IC and VC is 0 so that we can get these values. And for drawing it for the DC load line, I can draw like this. This is IC and we calculated this value, that is 2 milliamps. This is 2 milliamps and this is 12 volts. This is 12 volts. So if I connect these 2 points, you will get the DC load line. This is DC load. Okay. This is a procedure to draw the DC load line. Now, that is the first step. Okay. First, they said find out the DC load line. Then they said find out the Q point. If zero signal IB value and beta value is given to us. So they gave us the value of IB is 20 microampere and they gave beta value as 50, right? So in that case, this is the zero signal base current, zero signal IB. Okay, zero signal IB is given to us. So can we find out the zero signal IC? Zero signal IC. So as you know, IC is equals to beta IB, right? So beta is given to us is 50, IB is given to us is 20 microampere. So it will be what? 1 milliamps. This is the value of what? IC. That means for finding out the Q point, we should get the value of IC as well as VCE. These 2 points we again require it. Okay. So how we will find out the value of VCE? We know the equation, that is what? A VCC is equals to VCE plus ICRC. In that, we've already calculated the value of IC. Okay, RC we know. We also know the value of VCC, right? All these things we know. So what is that value of VCC? It was 12 volts. We have to find out the value of VCE. So I kept same. IC, we already calculated, that is 1 milliamps. RC in the equation, in the value is what? 6 kilo. So you can provide it as 6 kilo. Tell me the value of VCE fast. Tell me the value of VCE.
6 volt.
Okay. So now we got the Q point. What is that? IC is equals to 1 milliamps and VC is equals to 6 volts. We already drawn the DC load line, right? Like this. where the value was 2 and 12. It was 2 milliamperes and this was 12 volts. So this was the DC load line that we already drawn. Now for finding out the Q point, now this is Q points, okay? And IC is equals to 1 milliamps. That we calculated, right? This is we have already calculated. So if IC is equals to, and this is what 6 volts, right? So this is 6 volts and this is 1 milliamps. This point is a Q point. So by intersecting these 2 points, you can find out the value of Q point. This will be a Q point. So like that, you can find out the Q point and DC load line. Okay. We will solve some more questions regarding this. Okay. In our next lecture. Okay, that's all from my side. I'm now providing you these notes. If you have any doubt, you can ask.
Sir,
Yes.
sir, this is not regarding today's class, but you
Mhm.
had corrected the exam papers, right?
Yes, correct.
Yeah. So for that question on resistances, no, sir, where you gave the color coding and then you asked find the. Is there any like marks allotted for like given the color code, you have to find the actual resistance value, right? Is there any marks for that? Like out of 5, is that like 1 mark or 2 marks for finding the resistance?
Please repeat your question.
Yeah, sir. In that question for finding equivalent resistances when you're given the color coding.
No. After finding the equivalent resistance, no need of writing the color code. In one question, there was the means I drawn it and I said what is the value of A, B, C, D. There was one question on that you have to write down the colors.
Yes, sir. Yeah. But in my question, I was given like 2 color codes, and it was given find the equivalent resistance of these 2 resistors. Yeah. So
In that case, there was not any mark for colors.
oh, so for converting the color code into like actual resistor value, no
Huh.
mark.
But there was a circuit. You have to find out the circuit resistance, equivalent resistance. That
Yeah.
means first you have to calculate the value of resistance, and then based on that resistance value, you have to calculate the equivalent resistance.
Right. Okay, sir. Okay. Thank you.
Okay. Okay, I will take your attendance directly from you. Now you can.
Thank you, sir.
Thank
Thank you, sir.
Thank you, sir.
you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you.
Sir,
Thank you, sir.
Thank you.
thank you, sir. Sir, can you hear me?
Yes.
Sir, when should we apply for recat, sir?
There was some time you got in mail, na? You got one mail, I think. You check your mail.
Okay, sir, but it hasn't closed yet, right?
Actually, today is the date if you want re-evaluation and recap. You check in your mail, huh?
Okay, sir. Thank you.
Yes.